Hello everyone, and welcome to the CIV 398 Assignment 2. So I got some good news and some bad news for you guys. The bad news is Assignment 2 still is mainly focused on linear algebra. And I don't know about you guys, but I'm not the biggest fan of linear algebra. I'm more of a fan of the applications of linear algebra, which have to do with structures such as the stiffness matrix, the stress matrix, etc., etc. But good news is that's kind of coming up very, very soon. But it's not the good news about the assignment. The good news about the assignment for you guys is that 99% of the assignment can be calculated through Mathematica very, very simple. So if you guys want the easy way using Mathematica, the assignment will actually be a breeze for you guys. And because I know that many of you guys will opt for this way, I added the Mathematica code functions for a lot of the things that we're going to be discussing today. So if you guys want the quick, easy Mathematica way, just type in the functions I give you and you guys should be able to solve this assignment pretty quickly. All right, with that being said, let's jump into question 1. And question 1 says, find the determinant, the eigenvalues, and the eigenvectors for the following matrices. So we're given two matrices and it wants three different things: the determinant, the eigenvalues, and the eigenvectors. And if that wasn't enough, the question continues on and says, if the matrix is invertible, determine its inverse. And if the matrix is not invertible, determine its kernel. So we have kind of three extra checks that we have to do after finding the first three checks. And the first one is we're going to have to find out if the matrix is invertible. If the matrix is invertible, then we're going to have to find its inverse. And if the matrix is not invertible, we're going to have to determine its kernel. So basically 5 steps for each one of these matrices. So it's going to be quite a beefy question. But again, if you guys remember Mathematica, it'll be very, very quick. So the first thing that the question wants is the determinant. And the determinant of a 2x2 matrix can be found very, very easily. So you guys basically have two options at this point. The first one is you can do it by hand. So if m is equal to a1, a2, b1, b2, then the determinant is very simple to calculate because it's just going to be a1 times b2 minus a2 times b1. But as I mentioned, a lot of you guys are probably going to opt for the Mathematica solution for this. So option 2 using Mathematica is all we have to do is to find the matrix M. So to define that in Mathematica, we're going to have big squiggle brackets. These are the brackets at the end of M, the beginning and the end of M. And this is everything inside the matrix. And inside of those squiggle brackets, we got two subsets of squiggle brackets, and those are for the rows of the matrix. So within the first little subset of squiggle brackets, I got A1 and A2 separated by a comma. And then in the next subset of squiggle brackets, I got B1 and B2. So that's the first row of the matrix and the second row of the matrix. And once I define that matrix M, all I have to do is type in det of M or det of M to find the determinant. So again, another little fun fact about Mathematica operations is that, or the functions, is that they need a capital, so it has to be a capital D. If you guys do a lowercase d, lowercase det, nothing's going to happen at all. And the second thing is the function always uses square brackets. So after we type in capital DET, we're going to have to put square brackets, then we put our matrix M inside. And once you press Shift Enter, you guys should be returned with the determinant of M. So the second part that we have to do for all of those matrices is the eigenvalues. And this is where students kind of get a little bit more confused because determinants we've dealt with so much. It's a simple calculation and results in a nice little scalar. We like determinants, so they're nice and easy to do. But eigenvalues, well, they involve a little bit more work, and as a consequence of such, everyone doesn't like them. So to determine an eigenvalue, which we're going to denote as lambda, we need to solve the following equation, which is the determinant of m minus lambda I is equal to 0. So again, we have two options. The first one, we can do it by hand. And for a 2x2 matrix, you guys will see it's not bad. So again, if we define m, we can find the determinant of m as a1 minus lambda, and then a2. And then in the second row, we got b1 and b2 minus lambda. Well, we could simplify this because this is a determinant to get a1 minus lambda multiplied by b2 minus lambda, and then subtracted from a2 b1. And of course, that's all equal to 0. So if we look at this equation here, it's a nice quadratic equation. We can actually solve for this, and we should be able to find that there's going to be two lambdas. But then we can go to option 2. So if we have our matrix M defined, which we should already have it if you're using Mathematica for the determinant, there's a nice easy function in Mathematica to find the eigenvalues, and lo and behold, it's just eigenvalues of M. So again, same thing as the determinant, we need a capital E, and when we are defining our function, or sorry, our matrix M inside of the function, we have to use those square brackets between. If we use just circular brackets or squiggle brackets, it won't work. It has to be square brackets. So just like we found the eigenvalues of our matrix, we also have to find the eigenvectors of our matrix, which we're going to note as P. And there's kind of a couple ways we can solve this, but me personally, I just like to solve the equation m times the vector P, so m is our matrix, is equal to lambda times P, where those P's in both sides of the equation, they're the exact same thing. So option 1, by hand, we can say, okay, well, if I expand out that equation above, I get A1, A2, and then B1, B2, multiplied by P1, P2 is equal to lambda P1, P2. So if I look at this, I know A1 and A2 as well as B1 and B2 because those are given. Those are just part of the matrix we're given. And now that lambda, I should have two values of lambda based on finding the eigenvalues that we just did in the previous slide. So if we really look at this, we only have two unknowns, which are P1 and P2. So what we can do is we can expand this out to create two equations. So expanding it out, I get A1 times P1 plus A2 times P2 is equal to lambda P1. And then I get the equation, which is very similar just on the bottom, which instead of A, it's just B. And then at the end, it's P2 instead of P1. And all I have to do is really solve these equations. And it sounds simple, right? I got two equations. I got two unknowns, which are P1 and P2. But you guys will find quickly that there's going to be infinite solutions. Because remember, eigenvectors, there's many, many eigenvectors, infinite amount of eigenvectors associated with an eigenvalue. So what we have to do in this case is we're going to assume that P2 is equal to 1. And by doing that, we can look at the first equation and say, okay, well, if P2 is equal to 1, and I look at this first equation, my only unknown now is P1. So I can solve for P1. And with that, I can conclude that my eigenvector for that eigenvalue lambda is equal to P1 and 1. Now, as I mentioned, there's an infinite amount of eigenvectors. So what we usually do is we normalize them, and that's kind of the standard. If the question doesn't ask for you to normalize them, who cares? Just call it quits right now. But if the question asks you to normalize it, we're going to have to normalize this vector. So just a reminder that in its current state right now, unless P1, of course, is equal to 0, this is not normalized. And we're going to have to normalize it if the question asks for it. And then another thing we have to keep in mind is that lambda, we have two different values of lambda. So we just solved that equation above using our first value of lambda. But this has to be done again for a second value of lambda. So if we have two eigenvalues, then we should have two different eigenvectors. But again, we can always go option 2, which is Mathematica. So our matrix M, again, it's already defined. We're good to go. To find the eigenvectors, it's as simple as just typing eigenvectors of M. So our function in this case is eigenvectors. Remember, capital E, and we need those nice square brackets around the M. So if you guys can see really quick from Mathematica, all we had to do was to find the matrix, and then literally all we had to type was the det of M, eigenvalues of M, and eigenvectors of M. And you guys would have had all this already completed. But again, you should know the theory, which is why I like to kind of show you how you would do it by hand if you guys so choose. So now we're at a crossroads because the question said we have to basically find out if a matrix is invertible. And there's going to be one specific way to tell if it's invertible. But before we do that, let's just kind of talk about what are the implications of a matrix being invertible. So if a matrix M is invertible, it'll have something called an inverse, which we denote as M to the negative 1. And that inverse will be very, very important if you guys go on to later courses dealing with structural analysis with the stiffness matrix and stuff like that. However, if the matrix M is not invertible, it'll have something called a kernel, which we denote as the ker, K-E-R, of M. So you guys might be asking, okay, well, I understand that it'll either be invertible or not invertible, but how do we check? Well, to check if a matrix is invertible, we use the determinants because there's going to be two scenarios that happen. The first one is the determinant does not equal 0. So if the determinant is 9, or it can even be a negative value. So even if the determinant is negative 9, we say that a matrix is invertible. And since it is invertible, consequently it has an inverse. However, if the determinant of M is equal to 0, so this is kind of a very solid statement, the determinant of M is equal to 0 and not anything else, we can say that the matrix is not invertible. And in that case, it has a kernel. So let's discuss the case where a matrix is invertible. So if we find our determinant of M and we find out that it's equal to some number that's not 0, we can say that it is invertible. So that's what you guys will do in the assignment. We already know the determinant because that was kind of part A of the question. So then we just check, is our determinant equal to 0? Well, if it's not, then we can say, okay, this matrix has an inverse. So like the eigenvalues and eigenvectors before, there's two ways to do it. And the first option is by hand, because for a 2 by 2 matrix, finding the inverse is not too bad. We can say that the inverse of the matrix M for a 2 by 2 case is 1 divided by the determinant of the matrix, so 1 divided by the determinant of M. And this kind of shows you guys why if determinant of M is equal to 0, this whole equation is undefined because we're dividing by 0. But 1 divided by the determinant of M, well, that's just going to be some scalar value. And then we throw it into this kind of rearranged matrix. So if we look, we have B2 where A1 should be, and we have A1 where B2 is normally. So we do a little swap-roo on those two. And then we also add negative signs to A2 as well as B1. So for a 2 by 2 matrix, option 1 by hand, it's not too bad. Again, you guys should probably know where this stuff comes from. But for those of you opting for Mathematica, all we have to do is use the function inverse of M. So again, our matrix is already defined. If we want to find the inverse, all we need to do is type the inverse of M. And again, please note that the function itself has a capital letter to start, so that capital I, and then the M is surrounded by square brackets. You're going to want those square brackets around. So finally, we look at the other case where the matrix is not invertible. So if we did part A of the question and we found out that the determinant of M is equal to 0, we say that the matrix is not invertible, and as such, we can find the kernel of the matrix, or KER of M. So this one's also kind of a little more abstract to solve by hand. So what we need to do is we need to find a vector V that maps to the 0 vector. So in essence, we have M times V is equal to the 0 vector. Well, to solve that, all I do is I kind of substitute everything in, and I got A1, A2 on top, and then B1, B2 multiplied by V1, V2 is equal to the 0 vector. So from this, we find out that there's going to be two equations, but just like the eigenvector scenario, we're going to find that there is infinite solutions. So the easy way to do this is assume that V2 is equal to 1, and we can solve for V1. However, if we're doing Mathematica, we can again use a simple function, but this time the function's a little bit tricky. Remember, if we wanted eigenvalues, the function's name was eigenvalues. If we wanted eigenvectors, the function name was eigenvectors. And even for inverse, if we wanted the inverse, the function name was inverse. However, if you type in kernel into MATLAB and we try and find the kernel of M, well, Mathematica is just going to go, wait, what? What are you trying to do? Because kernel is also a very important computational term. And in Mathematica's case, it uses the kernel for computation, not for matrix operations. So if we want to find the kernel of a matrix, so what we're interested in, the function in Mathematica is actually called null space. So there's a capital N, a capital S, null space. And again, our matrix M is surrounded by those nice square brackets. So if we define our matrix M, we can actually solve this problem very, very fast. We just use our 5 functions to quickly determine everything we need to know. If you want to solve by hand, a little bit more work, but you make sure that you know the theory. So it's kind of up to you. If you guys know the theory and you just want to breeze through with Mathematica, by all means, that's what we want you guys to do. We don't want these assignments to be a burden on you guys. All right, so this concludes question 1 of assignment 2. I hope you guys don't find it too bad. Again, use Mathematica if you guys are struggling. Mathematica can do things really fast, really quick. If you guys want to do it by hand to enhance your theory of it, by all means, it's completely up to you guys. That's the nice thing about this class, is it's completely up to you guys. So thank you guys all so much for listening. I will see you guys in question number 2.